So picture this. You wake up to a phone call at 3 a.m. A security researcher just found your company's entire database of user profiles floating around on the public internet. You completely panic. You rush to check your AWS account, and sure enough, your Amazon S3 bucket is wide open. But how? You know for a fact you never clicked Make Public. Why did your files suddenly become public? Well, it's because S3 security is not just a single switch you can flip. It's actually a really complex web of overlapping permissions, and you just tangled yourself right up in it. It's almost never just one wrong click. It's usually a failure to understand how all these different security layers interact with each other. Okay, let's dive right into this explainer. I'm going to show you exactly how S3 permissions actually work in a real production environment, so you literally never leak data again. We're going to untangle this roadmap step by step: identity versus resource policies, the legacy ACL trap, blocking public access, presigned URLs and encryption, and finally, VPC endpoints and auditing. Section 1. Identity versus resource policies. The two doors of S3 security. You have to understand that Amazon S3 is inherently paranoid. By default, every single bucket, every object, and every sub-resource is strictly private. The only entity that can access the data is the AWS account owner that actually created it. It's kind of like a massive bank vault where even the bank manager needs to scan their badge just to peek inside. To let anyone else in, you have to explicitly open the door. And there are really two main ways to open that door. First, you've got identity-based policies. These are your standard IAM or identity and access management permissions. You basically attach a policy to a user, a role, or even a Lambda function that says, hey, you are allowed to read from this bucket. Second, you have resource-based policies. These are your bucket policies. You attach a policy directly to the S3 bucket itself that says, I allow this specific external account to access my data. Now, AWS looks at both of these doors. If either one has an explicit allow, you get in. But here is the absolute golden rule of AWS security. An explicit deny always overrides an explicit allow. Let me repeat that. Always. If your IAM policy allows access, but the bucket policy explicitly denies it, the request is completely blocked. Period. You can hold all the right keys in your hand, but if the system explicitly says no, there's absolutely no way you're getting in. Section 2, the legacy ACL trap, where developers fail. Now, here is exactly where people mess up. They try to share a single file with a different AWS account. But instead of writing a nice, clean bucket policy, they use an access control list, or ACL. Guys, ACLs are a legacy nightmare. If an external user uploads a file to your bucket using an ACL, they actually own the object, not you. You can't even delete a malicious file from your own bucket. You are essentially paying AWS to store someone else's locked safe. To fix this, AWS created a feature called object ownership. As a developer, you absolutely must set this to bucket owner enforced. Doing this completely disables all ACLs across your entire bucket. From that exact moment on, every single object is owned by your account, and access is strictly controlled by modern IAM and bucket policies. You essentially take the power back. Section 3. Blocking public access, the ultimate circuit breaker. Think about that for a second. You can permanently lock down your data right at the account level. AWS gives you the block public access feature, and it acts as this ultimate circuit breaker. If you turn this on, it literally does not matter if a junior developer accidentally writes a bucket policy allowing the entire internet to read your files. S3 simply overrides it and blocks the traffic. It completely saves you from human error. But wait, what if you are hosting a static website on S3? Well, for a website to actually work, you must disable block public access, and you must write a bucket policy granting anonymous read access to your HTML files. But imagine if you accidentally store your private user database backups in that exact same website bucket. Suddenly, your private data is public to the world. So the rule here is incredibly simple. Never, ever mix public and private data in the exact same bucket. Section 4. Presigned URLs and encryption. Secure temporary access.
Now, what's really interesting about this is, imagine this scenario. You have a strictly private bucket. Block public access is completely turned on, locked down tight. But you still need to let a customer download a specific PDF receipt, or maybe let a mobile app upload a video. How in the world do you do that when the doors are basically welded shut? Well, you use a presigned URL. Your backend code, which already has strict IAM permissions, generates a temporary cryptographically signed URL. You hand that link over to the client, and they have exactly 15 minutes to download or upload that single file directly to S3. You get to grant cross-account access without ever changing your bucket policies or exposing your backend architecture. It's exactly like giving someone a self-destructing VIP pass.
Now let's talk about encryption, because honestly, having access is only half the battle. You have encryption in transit and encryption at rest. To encrypt data in transit, you use a bucket policy with a specific condition that strictly denies any request where AWS CloudTrail is set to false. What does that mean in plain English? It means this forces all traffic to use secure SSL or TLS connections, completely rejecting anything that's unencrypted. And for encryption at rest, you face a massive architectural choice: SSE-S3 or SSE-KMS. SSE-S3 means Amazon automatically manages the encryption keys for you. It's totally easy and it's free. But SSE-KMS means you manage the keys using the AWS Key Management Service. So why does this matter? Because with KMS, every single time someone decrypts a file, that API call gets logged. You get this perfect audit trail of exactly who read your sensitive data and exactly when they did it. You don't just know the data is safe, you can actually prove it. Section 5. VPC Endpoints and Auditing. Securing the private subnet. You really need to watch out for this incredibly common architectural trap. Let's say you have an EC2 server sitting in a private virtual private cloud, or VPC, subnet. It has absolutely no internet access whatsoever, but it still needs to write application logs to your Amazon S3 bucket. How does it connect? S3 is fundamentally a public service, so if your server doesn't have internet access, your upload just fails. The application crashes and your logs are totally lost. The solution here? You absolutely must configure a VPC gateway endpoint. Doing this creates a secure private tunnel from your internal network directly to S3, completely bypassing the public internet so your uploads never fail. Okay, let's lock this down. 3 rapid takeaways for you. 1. S3 is strictly private by default. Make sure you use bucket owner enforce to disable those legacy ACLs. 2. An explicit deny always overrides an explicit allow, and block public access is your ultimate safety net. And 3. Use presigned URLs to grant temporary, secure access without ever exposing your actual bucket to the public. I want to leave you with one final warning. If you aren't absolutely sure who has access to your data right now, run AWS IAM Access Analyzer. It will actively parse your policies and alert you the very second your private files are mathematically exposed. So really ask yourself, if I ran that analyzer on your company's AWS account right now, what would it find?